Hello.
Yes, sir. हाँ सर.
Nikam sir.
I think.
Hello. Hello.
हाँ yes sir.
सुरू करा की.
हाँ 3ला सांगितलं सर.
Just dot 3ला
या
चालू
या.
करा की.
Yes.
YouTube वर असतील बाकीचे लोक त्यामध्ये.
Yeah. Some of them on YouTube.
Over, sir, shall we start?
Yes sir. Within 2 minutes we will start.
Chandarki sir is there? Whether he has
No,
joined?
he is joining. He is joining.
Okay.
Good afternoon all. I welcome you all for second session of the FDP. For second session, we have a speaker. Just I will introduce him briefly. Dr. Chandarki Imran Mushtaq Ahmed. Currently, he is working as an associate professor at NB Naule, Sinhagad College of Engineering, Solapur. He has completed his PhD from Dr. Babasaheb Ambedkar Technological University, Lonere, under the guidance of Dr. B.B. Singh sir. He is having a total 15 years of teaching experience. Out of that, 6 years to PG program and 15 years to UG program. 2 PhD students are pursuing their PhD degree under his guidance. He has published near about 20 research papers with 21 citations, 2 H-index and Patent index. Also, he has presented 8 papers, 5 in international conferences and 3 national conferences. He is having good hands on the softwares like Mathematica, LaTeX, MathCAD, Scilab, Pascal, Fortran. He is having few achievements. He's received Best Teacher Award in the year 2015 at NBN Senior College, Solapur. Then he worked for Union Public Commission in 2016. With this, he got a recipient of Council of Scientific and Industrial Research India grant for attending the conference at International Conference on Stochastic Process and Algebraic Structures from Theory Towards Applications, held during October 4, 2017 to October 6, 2017 at Maraldalen University and Stockholm University, Sweden. With this, he is a managing editor of Journal of Frontiers in Interdisciplinary Research and Technological Development. He has published 6 books also on the 6 books of mathematics. So this is the brief introduction of our today's resource person. Now I would like to request Dr. Imran take the charge and please start your session. Thank you. Yes, Chandarki sir. Hello. Chandarki sir, am I audible? Hello. Chandarki sir. Just a minute. Chandarki sir.
आपण काय करायचं आता बॅक मारून काय उपयोग आहे वाया जाणार आहे ना आपण काय करायचं आता काय 100 रुपये कोण येत नसते तो ते उलट काम होतं नाही रिचार्ज केलं संपल्या विषयी तिने ऍड व्हॅलिडी होऊ द्या ना होऊ दे रिचार्ज केले होते व्हॅलिडी ऍड होते ते आपल्या असं बोलत गेलं की आपलं काम संपलं ना हो हो हा
Chandarki sir, please unmute yourself.
काहीच प्रॉब्लेम.
Just hold on. Some technical. Within 2 minutes, we will start. Yes, hold on. There is a technical problem from speaker's side that may get resolved within short span.
Chandarki sir, for audio you can use your mobile.
Hello. Am I audible now?
Yes, sir, you are audible.
Yes, sir. Yes, sir. You are audible. Please start.
So, friends, let me first share my screen. Is it visible?
Yes, sir.
Yes, sir. Yes, sir.
Okay, so friends, first of all, I apologize for this interruption and for being what 1 or 2 minutes late for getting connected through this Google Meet. I don't know what is the problem. So let us start. So before starting, I would like to thank the organizers of this 1 week FDP on essential mathematics for engineers and researchers organized by the SK Nole Senior College of Engineering, Koti, Pandharpur. I especially thank Professor Shivaji Pawar and also Nikam sir and the Honorable Principal sir, Dr. Kailash Karande sir, for inviting me for giving this lecture on this occasion. So basically, today I'm going to talk regarding the computational methods. This is the outline of my today's talk. I will be talking on computational methods, then the definition and the concept of paired approximations. And I'm going to apply paired approximations for series solution to one of the problem in fluid mechanics. Then I'm going to introduce one more method, that is introduction to the homotopy analysis method, that is also called HAM. And then I'm going to apply homotopy analysis method for mixed convection bond layer flow which is again one more problem of fluid mechanics. Okay, so that will be the outline of today's talk. I'm going to discuss about the governing equations, mathematical analysis, and results and discussion, and the methodology used. Okay. Now, before starting, let me quote one sentence. Mathematics is a place where you can do things which you cannot do in a real world. That you all know. I came to know that there are a majority of the mathematicians attending this workshop, and God exists since the mathematics is consistent, and the devil exists since we cannot prove it. Okay. So with this, let me start with the actual presentation. Now, my first question to you is why we require computational mathematics. Okay, why computational mathematics? So we know that every research concept deals with the three parts. Okay, the first one is mathematical modeling, second one is solution of mathematical modeling, and third one is interpretation of the result. Okay, generally who are the doing research, they know that they need to go for the mathematical modeling. Now you also know that mathematical modeling is a translation of physical phenomena. There are so many phenomena. Okay, they may that may be a physical phenomenon. That may be a physical phenomena, chemical phenomena. That may be a mechanical phenomena. That may be anything. Any phenomena can be converted into equations, and that equations are called mathematical modeling. Okay, so that is mathematical modeling. And in 90% cases, whenever we convert the non-stationary things into mathematical equations, then it gives a differential equation or a integral differential equation. Now, you know that for knowing the facts regarding the phenomena, you need to solve that equations. That is, you need to remove differentiation integration. If it is a differential equation, you need to remove that differentiation. And if it is integration, you need to remove the integration. And if it involves both, in that case, yes, you need to remove both differentiation and integration. For removing differentiation, we require antiderivative. Okay, an antiderivative is nothing but the integration. That's why what we require to integrate the equations. Okay, we require to integrate the equation. Integrating the equation means you are solving the equation, means you are obtaining the relation between dependent and independent variables in terms of equations. Okay, so if you have a relation which satisfies the equation, is called what? Solution, and it is called closed form solution. And you know that for precise physical problems, okay, for precise physical problems, the solution in closed form exists. But for complicated problems,
Excuse
yes,
me,
we cannot
sir.
guarantee. Yes?
Yes, have you shared your screen?
Yes, I have shared. Already I have shared.
Which one? PPT is there or Google Meet screen is there?
No, PPT is there.
Yeah, no, it is not visible. Then we
So
are.
you cannot.
Yeah, we are getting another screen.
Just wait.
Yeah.
Is it visible now, sir?
It not.
Is it visible?
No, sir.
Now you check, please.
No, sir.
Sir, is it visible?
No, sir. No.
Okay, just wait. I am going to share it through my mobile. Hello?
Yes, sir.
Is my screen now visible?
Yes, yes.
Okay.
Yes, sir. It is now visible.
So let me. Okay, I don't know what is the problem with my PC. It never happened. Anyway, so I was talking about the physical problems. So for complicated problems, the closed form solution are not available, or we cannot easily find it. Okay, so for that reason, for the sake of easiness, as far as the engineers and scientists are concerned, they have moved to the approximate methods, that is the computational methods. Okay, so let me first discuss regarding why we require the computational methods. We require computational methods because for engineers in the past to rely on the analytic skills to solve significant engineering problems, and thus they had to undergo a rigorous training in mathematics. Okay. Today, engineers, on the other hand, have access to tremendous amount of computational power under their fingertips, and they mostly need to understand the physical nature of the problem and interpret the results. They also need to understand how calculations are performed by computers to develop an awareness of the process involved and limitations while avoiding any possible pitfalls. Analytic solutions methods are limited. Now let us have a discussion on limitations of computational methods. The analytic methods are limited to highly simplified problems in simple geometries. I think just now I talked about the same thing. So for simple, precise problems, what analytic solutions are useful. But if problems are complicated, okay, in that case, what this precise net will not work. Even minor complications in geometry can make analytic solutions impossible. That is, it is affecting the stability of solution of the problem. So if we change, suppose that we have simple problem, okay, if we change minor things in that problem, and if we seek analytic solution, what we will not be getting it. That is the meaning of this second statement. Engineering problems often require extensive parametric studies to understand the influence of some variables on the solution in order to choose the right set of variables. If solved for one physical problem, can be very easily applied for other similar problems. I'm not saying that's same problems. I'm saying similar problems. So if we have the codes, okay, if you
Hello?
have scheme, suppose we
Hello,
have a
voice is not
differential
clear.
equation.
Hello, sir.
Yes.
Hello.
Yes, sir. Actually, voice is not clear, so we are not able to listen.
Am I audible, sir? Or sir?
Yes, you're audible.
One of the participant, she is claiming that I'm not audible.
Ma'am, can you check your connectivity?
Okay, it's fine now.
Okay.
So if we succeed in adopting one of the scheme for solving, suppose one of the physical problem. For example, suppose we have physical model and we have solved that physical model of differential equation and we got a solution. And if we got a solution and with the help of some computational method like Runge-Gupta method or atom decomposition method or any other method like that, in that case, it will be easy if once we have codes and if we adjust the little things in the programming, we can get the solution of other similar problems. That is the advantage, and we can save heavy labor in doing the computational works. So once we do, yes, we can use it further for similar problems. Then computers and numerical methods are ideally suited for such calculations, and a wide range of related problems can be solved by minor modifications in the code or input variables. So same thing, we have computers, we have numerical methods, and we can suit such calculations for wide range of problems. Okay. Now, what is the use of computational methods? We can use computational methods for solving linear problems, nonlinear problems, linear problems of a differential equation, nonlinear problems of differential equation, simultaneous equations, so many things we can solve. So for solving linear simultaneous equations, okay, we can use the bisection method, Newton-Raphson method, we can use the secant method, we can use other methods like that. Okay. Then we can fit some points to the curve. That is the fitting of curve we can do with the help of computational methods. We can use the interpolation. That is, if you want to find the value of one variable, if you know other values, value of other variable inside a table, okay, we can use interpolation. That is for upper part, lower part, central part. So we can do that with the help of interpolation. So I'm not going to go into detail because you already know it. Then we can solve, that is, we can evaluate the different integrations. Okay, so with the help of computers and with the help of computational methods, we can evaluate definite integrations which are very much required for solving the differential equations. Then we can solve initial value problems of first order and second order differential equations. We can solve even the partial differential equations like Laplace equations, the wave equations, and some particular cases of Navier-Stokes equations also. Navier-Stokes equations are very complicated equations, but for some particular cases of it, we can even solve it with the help of the numerical schemes, that is computational methods, and the programming, that is computer codes. Okay. Now let me introduce the thing that is few of you might be knowing, that is called a paid approximate. Okay, we have used it for 3 of our papers, and that papers have got published in 2 or 3 papers have got published in one in elsewhere, other in Springer. So let me first introduce what is this paid approximate and what is its use. We know that if suppose we have power series, okay, so power series means it is having a summation a n x raised to n type of expression. Okay, so if we have that type of expression, and if you require a asymptotic case there, that is, we require the value of that expression at infinity. Okay, limiting case at infinity, what in the current form we cannot find out it. because there is no facility by putting x equal to infinity, we will be getting the answer. Okay, though the thing looks impossible, can we do with the help of the paid approximation. So before that, let us see what is the paid approximation and how to use it for dealing with the asymptotic behaviors of the problems. Now, what is paid approximation? Paid approximation are the particular type of fractional approximation to the value of function. So if you have a polynomial, we can express that polynomial in terms of two polynomials, the ratio of two polynomials. That is simply we call it as a rational fraction approximation. So you can see on the screen, we have a plus bx divided by c plus dx. Okay, so that type of expression we can write for any expression. So you can see equation number 1. So we have written a plus bx divided by c plus dx. Note that numerator is a polynomial of degree 1. Denominator also is a polynomial of degree 1. Okay, so it is a ratio of two polynomials of degree 1. Okay, now look at the equation number 2. Equation number 2 is Rx 1 plus 2x divided by 1 plus x raised to half. And what with the help of series expansion, we can write its expanded form like equation 2. So 1 plus x by 2 minus 5x square by 8 plus 13 by 16 x cube and so on like that. Then that expression can be written like equation number 3. Look at the LHS. LHS is what 1 plus 7 by 4x and divided by 1 plus 5 by 4x. Now, why I written this thing, that is RHS in terms of LHS, like a plus bx divided by c plus dx. So it is called the paid approximate 1. Okay, so I written this complicated expression 1 plus x by 2 minus 5x square by 8 plus 25 by 32 x cube minus 125 by 128 x raised to 4 plus 625 by 5 and 2 x raised to 5 and so on. That complicated expression as simple equation 1 plus 7 by 4x divided by 1 plus 5 by 4x. Okay, now these two equations or these two expressions are equivalent. Now what is the advantage of the LHS? The advantage of the LHS is I can take x common from numerator and x common from denominator. And you will find that what x will get cancelled, and in the first term of numerator, I'm having 1 by x, and a first term of denominator is again 1 by x. Okay, and if I put x equal to infinity, yes, we will find that 1 upon infinity is equal to 0. So numerator first term is 0, denominator first term is 0, and the second term is now free from x. So it is simply 7 by 4 divided by 5 by 4. The answer will become 7 by 5. So we observe that if you take limit extends to infinity of equation number 3 or equation number 2, the expected answer from this series is not possible, but with the help of paid approximation, it is possible. The answer I can say is 7 by 5. So that is the advantage of paid approximation, and this we have used for one of the problem of fluid mechanics. Okay, and we have taken this motivation from a paper of Wazwaz. Okay, W. Wazwaz. Now let us see what are the paid approximation. Now here we have used paid 1. Paid 1 means paid 1 stands for a numerator polynomial is having degree 1, a denominator polynomial is having degree 1. You can use paid 2, you can use paid 3. So the accuracy of the answer mostly will be depending on how higher is the degree of numerator and denominator. If you use lower degree terms, you will be getting lower accuracy. If you will be using higher degree terms, you will be getting higher accuracy. As far as accuracy is concerned, it is up to you whether to use third paid or paid 3, paid 4, paid 5. So for our purpose, for our desired accuracy, we use what paid up to paid 3 maximum. Now, I think just now I discussed. So same thing. This is the paid 2. So numerator is having power x square and denominator is having a power 2. So both are having power 2. So it is called paid 2, equation number 4. So it is paid 2 of equation number 2. Okay. And see, in equation number 3, we have written paid 1. Paid 1, and equation 4 is paid 2. Okay. and what its value will be 1.41420 if you find limiting case. Okay, so for page 2 to page 3, what you can approach towards more and more accuracy. Now let us define the paired approximations. So what is paired approximations? We denote the LM paired approximate. How do you read it? LM paired approximate. L cross M paired approximate to AX. So AX is a polynomial. AX is a function. AX, it is not necessary that every time we should have polynomial. Sometimes we may have function there also. So AX is a function. Okay, so paired approximate LM of that function AX is denoted by L paired LM paired L slash M is equal to PL of X divided by QM of X. So PX is a polynomial, QX is also polynomial. L stands for degree of PX and M stands for degree of QX. So let me have feedbacks whether you are getting or not. Just put some comments. If I'm slow or fast. Am I audible?
Yes, sir, you are audible.
Shall I continue?
Yeah.
If there are any comments, then just inform me so that I can answer it. Okay.
Yes, sir.
So please do it for me.
Yes, sir.
Okay. So we denote the paired LM as PL of X by QM of X. Okay. So PL of X is a polynomial of degree L and QM of X is a polynomial of degree M. But for our problems, we have taken L is equal to M. That is degree of numerator we have kept same as the degree of denominator. Now suppose that AX is a polynomial. Okay, AX is a polynomial. Suppose AX is a polynomial given like summation I from 1 to infinity AI X raised to I. Okay, then it determines the coefficients of PL of X and QM of X by equation AX minus PL of X divided by QM of X is equal to order of magnitude of X raised to L plus M plus 1. Okay, since we can obviously multiply the numerator and denominator by any constant and leave L by M unchanged, we impose the normalization condition that QM of 0 is equal to 1. Okay. That's why they will not be having a common factors. Now let us see how we have applied the paired approximation. This is our paper. So now I'm going to talk on the second part of this talk, that is on paired approximate series solution of MHD flow equations with heat and mass transfer due to a point sink. Okay. Now in this we have used the similarity boundary layer equations. What is similarity boundary layer equations? We have converted the boundary layer equations to the nonlinear ordinary differential equations. So you know that the Navier-Stokes equations are most complicated equations. They have not solved for the general case. For particular cases of Navier-Stokes equations, we have some sort of solutions. But for general case, we don't have solution. We are waiting for solution. So many institutes are working on it. Still, they haven't got a positive result about the solution of general case of NS equation. These are called NS equation, Navier-Stokes equations. These are the famous equations, and these are the set of nonlinear equations which are complicated. Okay, and it involves the continuity equation, which is like what your del dot V bar is equal to 0. Okay, if your flow is solenoidal. Okay, maybe engineering faculty members are knowing this. So del dot V bar is equal to 0. It is called what? A solenoidal vector field. Okay, so that is the first equation of that Navier-Stokes equation, and remaining the three equations are the potential equations or accelerating equations of it. Okay. Now we have considered the similarity boundary layer equations governing the hydrodynamic fluid steady incompressible laminar boundary layer flow. For a point sink, so there is a sink here. We then applied a magnetic field, heat and mass transfer. So we have heat and mass transfer also, because we will be having that differential equations pertaining to the heat and mass transfer. The series solution method has been effectively implemented to a related integral differential equations. I think in my commencement, I started with talking about differential equations, and suddenly I approached to integral differential equation. So here, what we will be approaching towards integral differential equation. Okay, so a series solution method has been effectively implemented to a related integral differential equations. Okay, how that we are going to see. The condition at infinity is applied to a related paid approximation of the obtained series solution. So just now I think I talked about the paid approximation. So we are going to apply the condition at infinity. Okay. The features of the flow characters, heat and mass transfer have been analyzed and discussed with respect to the pertinent parameters, wise magnetic and suction injection parameters. So we have some graphs and we have some comparisons about our results and validation part. So we have found that the magnetic field here increases with the skin friction, but it reduces the heat transfer. That is the conclusion. So that we will discuss at the end. So this is the physical model. So there is a point sink at r equal to 0, axis symmetry. Axis of symmetry is there. The bondular flow you can see. Okay. So this is the physical model of the flow. These are the Navier-Stokes equations. So Ru differentiation with respect to R, Rw differentiation with respect to Z is equal to 0. So equation 11, 12, 13, 14, 15 with the boundary condition 16. Okay, so these are the actual Navier-Stokes equation, and that we have converted with the help of equation 17. These are the similarity transformations. So we have introduced the similarity variables as eta. Okay, psi is the stream function, and then M is the magnetic parameter, PR is a Prandtl number, KW is a suction injection parameter, and SC is the Schmidt number, and G eta is a concentration variable. U is a dimensionless velocity of the flow. So using this transformation, small g of eta is heat transfer. So using these transformations, equation 11 to 16 with the help of 17, yes, will get reduced to equation number 18, 19, and 20. Okay, so equation 18 is called the Tucker model. F triple dash minus F double dash plus 4 1 minus F dash square plus M into 1 minus F dash is equal to 0. And it is having association with the two more equations, that is G double dash minus PR F G dash equal to 0 and G double dash minus SC F G dash is equal to 0. Here F of 0 is equal to KW. Here KW stands for the suction and injection. Okay, if 0, there is no suction injection here. So if KW is less than 0, it represents a suction, and greater than 0 represents a injection. Okay, so for both cases we have studied this problem. So we have equation. It is also called the Falconer-Scan type equation. It is not exactly a Falconer-Scan equation. Falconer-Scan equation is given by F triple dash plus F double dash plus beta 1 minus F dash square. Okay, so this is Falconer-Scan equation, which is being derived by Falconer and Scan both simultaneously in the year 1947. Okay, after theory of boundary layers and Prandtl boundary layer theory is revealed. And this factor M into 1 minus F dash is due to Tucker. That's why it is also called Tucker model. So F triple dash minus F double dash plus 4 minus F dash square plus M into 1 minus F dash is equal to 0. What it is called the Tucker model. So this is the main equation that we intend to solve with the help of the series paid approximation. Okay. Now the second two equations, that is G double dash minus PR F G dash equal to 0. So these two equations are almost same. In first we have PR, which is related to your heat, and in second we have a Schmidt number, which is related to your concentration. And we have the boundary conditions given by 21, 22, and 23. So we have obtained from 16 Okay, the boundary conditions 21, 22, 23 with the help of the again similarity transformation 17, which is given in this on this slide. Okay. Now, what we had done, so we had taken simply equation number 18. You can look at equation number 18. Simply, we have integrated this equation, okay, from 0 to eta. Okay, so you can check it out. Here, we have set, okay, we have said f double dash of 0 is equal to beta naught, which is our skin friction coefficient. F double dash of 0, what we have said, it is equal to beta naught. So it is unknown. Okay, we are now going to find out this beta naught with the help of paid approximation. Many of the authors, many of the researchers, they find out this beta naught with the help of other methods like shooting method or RK method or some coupling of 2 or 3 methods. But here we are going to find out with the help of paid approximations. Okay, so f of 0 is equal to kw. Already it is there in a boundary condition. So you can check it out, equation number 21. F of 0 is equal to kw, f dash of 0 is equal to 0, and f dash of infinity is equal to 1. What we have taken as it is, and extra thing we have taken here, and we have said that is f double dash of 0 is equal to beta naught. So this beta naught is the thing that we are going to now emphasis on. Okay. So f dash of infinity is equal to 1, and now I'm going to integrate equation number 18. Okay, from 0 to eta. So if you integrate, yes, equation number 18. But before integrating, what we will write that equation by writing f triple dash on one side and remaining terms on other side. So we get equation number 26. Okay, so it is simple algebra I did here, and then let us integrate this from 0 to eta. If I integrate from 0 to eta, f triple dash will become f double dash and minus f double dash of 0. And what we have said that f double dash of 0 is equal to beta minus beta on that side, it becomes plus beta, and the remaining terms will look like this. Okay, so 26 will become 27. So f triple dash becomes f double dash, and minus beta on that side, it becomes plus beta. And what f double dash is under integration. 4 1 minus f dash square is also under integration. M minus m and minus 4. Okay, so it is it will get joined with the eta term because minus 4 is constant, minus m is also constant. So minus is outside, and 4 plus m into eta is outside. Okay, and if you put upper lower limit, we get eta on here. Okay, and then minus mkw. Now what is this mkw? Okay, so this mkw is f of 0 term. Okay, f of 0 is equal to kw. So here we got here mkw. Okay. Now remaining two terms, that is the minus plus f dash square dt, and the second term, that is your f double dash integration from 0 to t will be as it is. Now let us go for a second time integration of it. Okay, so f triple dash becomes f double dash. If you further integrate it, okay, so it will look like equation 28. So equation 28 will be, yes, f dash of eta minus, yes, it will become what? F of 0. And f of 0 is nothing but what? Your kw. Okay, so second term integration will give you 28. You can verify. Okay, I'm going to provide you this slide or this presentation. You can verify it and you can use it for your problems. So we get 28. And then third time integration gives you f of beta is equal to kw plus this type of expression. Okay, so we get this 29, equation 29. And now here, if you look at the last three terms, okay, last two terms, you will find that there are more than 2 integrations. So in 3 terms, there are more than 2 integrations. So 0 to eta, 0 to eta. Here also we have what? 0 to eta, 0 to eta. So triple integrations are there in 2 terms, and double integration is there in. Okay, so actually it is not double or triple integration. It is thrice integration and twice integration. So there is a difference between a thrice and triple integration, and twice and double integration. Double integration is different concept. Here, same thing, we have integrated twice and thrice. Like multiple times we differentiate. Here, multiple times we have integrated. So we got equation 29. And what now I'm going to use one concept, okay, from the integral differential equation, okay, that reduces the triple integration to single integration. So triple integration, what will get reduced to single integration with a factor eta minus t bracket square divided by 2 f double dash. Here also we have eta minus t bracket square divided by 2. Here it was already we have 4, so 4 divided by 2 that becomes 2. And what double integration will get reduced to single integration 0 to eta minus t f of t dt. Okay. Now this is equation number 30. Now what I'm going to claim, let me define a function f of eta. Suppose that you have a function f of eta. Let us claim that our solution is a power series given by 31. So suppose that f of eta is solution and it is given by what? A0 eta raised to 0, A1 eta raised to 1 plus and so on. That is summation n from 1 to infinity. Yes, an eta raised to n. So it is an infinite series. So we have claimed that f of eta, which is a polynomial, which is a power series, is a solution of our equation 30. Okay, which is equivalent to what? Solution of equation number 18. That is Tucker model that I talked about. Okay. So what I'm going to do now is I'm going to put the value of f of eta here at the first place. So I'm going to put f of eta at the first place. I'm going to differentiate it once and twice. So f double dash I'm going to put here. Okay, and f double dash I'm going to put here, and f dash bracket square I'm going to put here. F of eta is there. So this polynomial, you know that differentiation of f of eta, okay, will reduce the power of power series. So if f of eta is having what power equal to n, it will get reduced by 1. Okay, if you differentiate it once. If you differentiate twice, it will get reduced by 2 power. Okay. So by that construction part, yes, I will substitute the value of f of eta in terms of a series, f dash of eta in terms of a series, f double dash of eta in terms of a series, and then I am going to simplify it with the help of what? Mathematica. So see what I did. So here is your LHS. If you look at the LHS, A0, eta A1, eta square A2, eta cube A3, plus eta raised to 4 A4, plus eta raised to 5 A5, plus and so on. So this is f of eta. This is a power series. And on other side, what we have? So first look at that, kw plus beta, first term as it is, second term as it is. And in third term, yes, at the place of f of eta, I replace it by A0 plus t A1 plus t square A2 plus and so on up to infinity. And then f double dash, so double dash starts with 2A2. Okay, if you differentiate the polynomial, look at that. First term is 0. Okay, if you twice differentiate, second term also will be 0. And second derivative will be what? 2A2. So we have started with 2A2. Look at this. We have started with 2A2. So first term is f and second term is f double dash. So f double dash and eta minus t bracket square divided by 2 is there. And look at the fourth term, eta minus t bracket square, and it is multiplied by f dash. What is f dash? F dash obviously will start with a1 plus 2ta2 plus and so on. Okay, and then here again what we have m, look at the last term of 32. Last term is what? M 0 to eta minus t. Yes, it starts with a0, means it is which term? F. So let me take a feedback whether you are getting. Are you getting me? Power sir? Please ask the participant.
Yes, sir.
Okay, so shall I continue?
Yes, sir.
Okay, so we are at 32 equation, and then these equations will be simplified with the help of Mathematica. Note that our A0, A1, A2, A3 and so on, what they are unknowns. Okay, along with the value of beta naught also. So we have so many unknowns at this stage. So beta naught is unknown, A0 is unknown, A2 is unknown, and so on. All the things are unknown. Okay, now what I'm going to do? Yes, I'm going to simplify it. Okay, so on one side we have polynomial. One side, if you look at the LHS, look at the 32 equation. 32 equation is A0 plus eta A1 plus eta square E2 plus and so on. So one side is a polynomial. Okay, and look at the RHS. RHS is not a polynomial. It is what it is involving integrations, and that integrations are to be evaluated. So with the help of Mathematica, it is not manually possible to evaluate these integrations. Without Mathematica, you cannot imagine it. Okay, so evaluation is possible with the help of Mathematica. So I use Mathematica programming and got evaluation of RHS. LHS is already a polynomial and equal to KW. So this is simplified form. So you can see there are so many terms. Okay, I've gone up to eta raised to 13. But in actual programming, I've gone up to eta raised to 53. Okay, so here I have shown eta raised to 13, but due to space problem, what I had taken only eta raised to 13 here. But while executing, I use up to eta raised to 13 because I found the stability there. So my physical and boundary conditions are behaving properly, and that's why 53 eta raised to 53 is feasible. Okay, that's why I use that one. But here while showing, I have shown up to eta raised to 13. So you can see that LHS is also polynomial, RHS is also polynomial. You can see A0 will be directly equal to KW if you compare. So eta square, eta cube, and so on. Here also we have eta square, eta cube, eta raised to 4, eta raised to 5, and so on. So you can see LHS is polynomial, RHS is also polynomial, and once both are polynomial, we can compare the coefficients of like powers from both the sides. So if we compare with the help of, again, what I'm going to do Mathematica. So using Mathematica, we can compare, and after comparison, yes, I got these results. But I got the value of A0 is equal to KW. The value of A1 is equal to 0 directly. The value of A2 is equal to beta naught divided by 2. Note that still this beta naught is unknown. A3 is 1 by 6 minus 4 minus m plus KW beta naught. This beta naught is unknown again. A4 1 by 24 minus 4 KW minus KWM plus KW square beta naught plus MW m beta naught. So you can see that I got A0, A1, A2, A3, A4, A5, A6, A7, and I have gone up to A23. Okay, so as far as the power of eta is concerned, I have gone up to 53, and as far as unknowns are concerned, I have gone up to 823. Okay, so there is a theory behind it what we should go up to that one. Okay, because I had tested the stability of the problem, stability of the solution. So my solution was behaving well. Okay, behaving as expected for eta raised to 53 and for A23, and that's why I use that one. So I got these values of A0, A2, A3, and so on, A7. Once I got this, the only unknown remain now is beta naught. So see, if you get beta naught, okay, the remaining pertaining parameters can be varied, and we can find out the solution of f of beta. We can find out f dash of beta, that is the velocity profile, and we can also find out f double dash of 0, that is skin friction coefficient. Okay. So after calculating, yes, f of eta, which is equal to A0 is KW, eta square B0 by 2. So this is your A1, eta cube divided by 6 minus 4 minus m plus KW beta naught. So this term is nothing but your A3, and so on. So we have substituted all that A0, A1, A2, and so on is up to A23 in f of eta, and we got this series solution, and that's why the title of the paper is the series solution of paired series solution of the MHD equation of heat and mass transfer kind. So we got f of eta. Simply again using Mathematica, we have differentiated. We got f dash of eta. Okay, now this f dash of eta is very important, because this f dash of eta I'm going to take it to infinity as eta tends to infinity. So I'm going to take limit of this f dash of eta as eta tends to infinity. If eta tends to infinity, yes, we have f dash of eta is equal to 1, and which will help us in using paired approximation of this f dash of eta in dealing with and finding the value of beta naught. Okay. So after getting f dash of eta, using the concept of solution, referred by Evans, book of Evans, we obtained the solution of G of eta, that is heat equations. Okay, that is equation number 19 and 20, heat equation, and the second equation is concentration equation. So we got both that solutions. So that is very simple. See, if you know value of f here, we can find out all of the things of 37 RHS. So G of eta will be known to you, G dash of eta will be known to you once you know what is f of y. So f of y is known to us. Okay, f of y is given by 35. Okay, so f of y is 35. So f of y or f of beta, we can find out what G of beta, we can find out G dash of beta, we can find out G dash of 0, which is the heat transfer parameter, and we can find out capital G of beta, capital G dash of beta, and capital G dash of 0, which are pertaining to the concentration parameters and concentration equations. Okay. Now, let us once again come to the paid approximates. Okay, so we are going to use the paid approximates, paid approximate L by M, which is a ratio of PL of eta to QM of eta. Okay, now what I did, look at carefully at the equation number 41. Okay, what is equation number 41? If you look at the equation 41, RHS is A0 plus A1 eta plus A2 eta square. Okay, note that on LHS you have second term 1 plus B1. Okay, look at this term. Look at the second term, 1 plus B1 eta plus B2 eta square. So if you take this term onto the what LHS, RHS, what we have A0 plus A1 eta plus A2 eta square and divided by 1 plus B1 eta plus B2 eta square. So actually what I did in this equation 41 is, this is your f dash of eta. What is f dash of eta? Beta naught eta plus eta square by 2 minus 4 minus m plus kw beta naught plus eta cube by 6 minus 4 kw minus kwm and plus kw square beta naught plus m beta naught. So this term is nothing but f dash. So this is your f dash. Okay, and this f dash I written as a what? Paid 2. Is it paid 2? Is it paid 2? A0 plus A1 eta plus A2 eta square and divided by 1 plus B1 eta plus B2 eta square. So that is paid 2. Note that this A0, A1, A2 can be very easily found. Okay, see what manually we can do? We can multiply these two polynomials. Okay, so if you multiply LHS first polynomial with the LHS second polynomial, if you multiply these two, if you simply open the brackets, yes, you will be getting beta naught into eta into 1 is equal to A1 eta. So we can compare the coefficients, and after comparing the coefficients, so LHS is the polynomial, RHS also is the polynomial. If LHS, RHS are both polynomials, we can guess values of B1, B2 and A0, A1, A2. And once we got B0, B1, B2 and A0, A1, A2, yes, that what we will be getting like this as shown in 42. Okay, and the only unknown is beta naught. Okay, so the only unknown is beta naught. And how to find beta naught? So I use here what paid 2 of this polynomial. Which polynomial? The first big polynomial, beta naught eta of equation 41. Actually, it is your f dash. So this f dash is equal to what? RHS of 42. F dash is equal to RHS of 42. If you take limit n tends to infinity, the RHS becomes 1. And if you cross multiply and if you simplify it for beta naught, your value of beta naught, which is equal to f double dash of 0, will become 2.3928. Okay, so if you use higher values of paid, that is a paid 3, paid 4, yes, you will be getting more and more accuracy. So for easiness, okay, what I have taken paid 2, but I use paid 3 and paid 4 for dealing with the calculations and for writing the concluding remarks and results. So this is the table. This is a table which reveals the value of beta naught. Okay, here we have calculated the value of beta naught. So these are the values of beta naught. skin friction coefficient for different values of m. Note that m is greater than 0. And here, this table is a table for Kw less than 0. Okay, that is for suction. So Kw less than 0 is here denoting suction. So m is equal to 0, m is equal to 0.5, and m is equal to 1. And Kw less than 0, sorry, that is injection is Kw is equal to -2. Okay, we got paid 2, 2, paid 3, 3, paid 4, 4. Again for m equal to 0, Kw equal to -1, paid 2, 2, paid 3, 3, paid 4, 4. We got these values, and you can see that the values are very close. Present case and see the case of Tucker. The values are very close, and that is the validation of our results. Okay, so whatever we did is correct. That is the validation part. We have second table also. That is for Kw greater than 0, but I not included here. So this is the result and discussion. Today I'm going to just talk on what is the method here we applied, because we are dealing with the methodology of computational method, not with the result that we obtained here. So this is second table, that is a Kw greater than 0 for f double dash of 0. Again, we are compared it with the Rosenhead and also with Tucker et al. So for two cases we have compared our results, and we have found that the results are very close in agreement. So you can see the values are 2.27229 and 2.2728 and 2.273. So our results are very, very close in agreement with the authors reported in 1986 by Tucker and 1963 by Rosenhead. Okay, so these are the values for paid 2, 2, paid 3, 3, and we have taken average of it, and average value is very close. Okay, so that is the second table, and then we have result and discussion and all that things. I'm going to skip it because I need to go for the second method also. So we are now discussing just methodology. These are the results and discussion part. So what is happening with the skin friction coefficient and all that. Just wait, there is some problem. So we have graphs here. Okay, so with the help of Mathematica, we have graph for skin friction coefficient with the Kw for range of m starting with 0 to 2. Okay, and we have combined it with the Tucker et al. And you can see the values are very close. Okay, our profile and the profile of Tucker, they are very close. Okay, so that is the confirmation that the result and the things that we did is correct. So this paper has got published in the year 2015 in elsewhere. Now let me talk about the second method, that is a very hot subject now going on, that is the HAM. It is in short called HAM. HAM is what? Homotopy Analysis Method. Pawas, before starting with the last part of this talk, is there any question from the participants? Hello?
Yes, sir.
Is there any question?
Yes, anyone have any question? Participants? If you have a question, you can unmute yourself and ask.
Yes, if there is any question, you can ask. It should be a two-way communication.
Sir, hello.
Yes, yes.
Sir, I have one question.
Yes.
Can we solve integral differential equation by using Matlab or any other software?
Yes, definitely we can. But the thing is that method and the program should be suitable. Okay, that should match. I hope that you got my meaning that I want to say. Okay, the method and the program that you are using should match. Should match in the sense it should be compatible. Okay. So you know that there are so many methods. I'm going to give one example, simple example. Okay, we have so many methods for solving equations. linear equations and algebraic equations, transcendental equations. Yes or no? By bisection method, by Newton-Raphson method, by secant method. Okay, there are so many methods like that. Agreed?
Yes, sir.
So why we have that much method? If one method is working, yes, you ask yourself why we require that much methods. Okay, so scientists have what should have stopped at one method. Okay, one method if it is one method if it is developed and if it is with you, why we should go for third method, fourth method, fifth method? Why they are developing multiple methods for same scheme? For solving equation, we have so many methods. Even you can see for solving simultaneous equation, we have what Gauss-Seidel method, okay, Gauss elimination method. There are so many methods like that. Gauss-Jacobi method. For solving differential equations of first order, first degree, numerically, we have Euler's method, we have RK method, we have Euler's modified method, and we have so many predictor-corrector method. So we have so many methods like that. So my question is, why we require that much methods? If one is working and it is doing well, why we require that much methods? That is my question. So the answer to this is, what few problems are suitable, are compatible with few methods. Okay, we cannot guarantee that. Yes, every problem will have same sort of solution by same method. So you cannot claim that what if all the differential equations can be very easily solved by a single method. Okay, so some simple equations can be solved by Euler's method. Some more complicated equations can be solved with the help of Euler's modified method. Okay, more complicated equations can be very easily solved by your RK method and so on like that. Predictor-corrector method. See, predictor-corrector method is very complicated, but still we are requiring it. Why we are requiring? For getting the stability in the solution. Okay, so if you are using Euler's modified method for very complicated problem like this problems of fluid mechanics, it won't work. Okay, it won't work. So you require there which methods? The compatible methods, and compatibility can be checked. Okay, by initial and boundary condition, and whether we are getting same graph or not. If graphs are working well, and there are some mathematical tools. Okay, so using that, we can predict, okay, this method can be applied to this differential equation and it is compatible. I hope that what I have given you answer.
Okay.
Is there any answer? Is there any question?
Yes, there is one more in chat box.
Yes.
Is there any limitation on PD approximation method?
Limitation. Yes, limitation is regarding the complexity of the problem. See, limitation, definitely there is limitation of this method. Your differential equation or your integral differential equation should be autonomous. Autonomous means it should not involve the independent variable. Okay, explicitly. Okay. Your independent variable should not be part of the differential equation explicitly. If it is there, then there is some difficulty. Okay, or there is a problem with your stability. Okay, so expected answers, the answer obtained will not work as expected. That is the problem, and that is the limitation of this method, paired approximation method. And the second limitation is regarding the length of answer. Okay, so it is not a closed form answer. It is very big answers that we are getting with the help of paired approximation method. Yes.
Okay. Sir, paired approximation method, it is applicable only for one equation or set of equations?
It is, actually, whenever we have equations, if the equations are simultaneous, that is, they are interlinked. Okay, they are also called coupled equations. Okay, so if the equations are simultaneous or coupled, in that case, if you solve one equation, okay, and if you know the method of solving remaining two equations, suppose I have one equation, as that of my case, if you look at the first equation, equation number 18, okay, so I'm going to show it to you again. So if you look at the first equation, it seems to be very complicated, but as compared to the remaining two equations. So if you solve the main equation, okay, you can solve remaining two equations very easily. So we can solve what multiple equations, coupled equations, okay, as per our convenience. But I cannot guarantee you that, okay, anything can be solved. I cannot guarantee you.
Okay.
So you need to test so many things. Sometimes the initial and boundary conditions pertaining to the problem, physical problem, they may get satisfied to the answer. Sometimes they may not get satisfied.
Okay. Got it. Yes, Chandarki sir. Hello. Chandarki sir, am I audible? Are you there, Chandarki sir? Hello. Chandarki sir. Chandarki sir, are you there? I think he has left the meeting. Chandarki sir, am I audible? Are you there?
Yes, I'm there. I got a call. That's why the this meeting got disconnected. Am I audible now?
Yes, you are.
Okay, just wait. Now you can see my screen. So is the screen visible?
Yeah.
Okay, so I was talking about this equation number 18. So see, this equation is a nonlinear. So even though it is look like a very easy equation, but we cannot solve it analytically. Okay, analytically, what its closed form solution is not possible. That's why we have gone for approximate methods. There are so many methods reported by so many researchers, numerous researchers, but the problem is few are having with the less accuracy, few are having a good accuracy. Okay, so we have claimed that our accuracy is good because our results that we compared with the pertaining parameter to other authors are behaving good. Okay, so they are in good agreement. That's why. So if you solve equation number 18, okay, we can solve remaining two equation 19 and 20 also. Okay. So is there any other question, Power sir, from on my behalf? You can ask the question.
No, sir.
If there is.
Yes,
So shall I continue with the last part?
Yes.
So in the last part of this talk, okay, I will be dealing with a very important method and which is a very hot subject nowadays. That is called homotopy analysis method. Homotopy, this word came from the subject called or topic called topology. You might be knowing topology. Okay, I think at a postgraduate level, every university is having one course that is called topology. So this word homotopy comes from what topology, homomorphism of a topology. Okay. So let us discuss what is homotopy and let us have a discussion on how we apply the topology. So let us have let us see what is this concept of homotopy analysis method. So there are some analytic techniques for nonlinear problems, such as a perturbation technique. So perturbation technique, you know that perturbation technique involves use of a very small or very high parameter. Okay. Then we have perturbation techniques, and a lot of important properties and interesting phenomena of nonlinear problems have been revealed with the help of perturbation techniques. Then perturbation techniques are essentially based on existence of very small or very big parameter, okay, or large parameter or variable called perturbation quantities. So if that type of parameter, very small or very big or very large, if we have that type of variable or that type of parameter involved in equation, then only we can use your perturbation methods. Okay. However, it is the perturbation quantity that brings some serious restrictions to the perturbation techniques. So perturbation technique we can use, okay, but there are some serious restrictions on perturbation techniques. What is that? Firstly, it is impossible that every nonlinear problem will have one sort of small or large parameters. We cannot guarantee that every problem will have that type of a very small parameter. Okay, you know that Reynolds number in fluid mechanics we use Reynolds number. Okay, if Reynolds number is very high. Okay, sometimes Reynolds number is comparatively less. But we cannot guarantee that every time we will be having some extreme cases, very less, very high, like that. So we cannot guarantee every time whether we have very small or very high parameter involved. The next thing is we can use other methods like atom decomposition method, and then we can use some other analytic methods, but they have some limitations and they have some accuracy problems. Okay, they don't seem to be having giving results as expected. Okay. So with this reason, what we should learn this homotopy analysis method, which seems to be behaving like analytic method, because it is giving you a closed form solutions. How it is doing closed form solutions, okay, and how. So I think we were here on this slide. So by means of perturbation techniques, a lot of important properties and interesting phenomena of nonlinear problems have been revealed. Perturbation techniques are essentially based on the existence of a small or large parameters or variable called perturbation quantities. However, it is a perturbation quantity that brings some serious restrictions. I think just now I talked about to the perturbation technique. Firstly, it is impossible that every nonlinear problems, we cannot guarantee that such parameters will exist. Like perturbation techniques, we can use like perturbation techniques, non-perturbation methods such as artificial small parameter methods, delta expansion method, then Adamant's decomposition method, shooting method. They also have some serious limitation and restrictions in them. Thus, none of all above can provide us with a convenient way to adjust control convergence parameter. So we are again talking about control convergence parameter. What is control convergence parameter? So it is a parameter which is giving us a idea regarding for what value of that parameter our solution is stable. What do you mean by stable solution? We can say our solution is stable if it is behaving as expected by the physical model. Okay. On the account of this, the Chinese scientist Shizong Liu, reported a very famous method. He has developed a very famous method that is called homotopy analysis method, in his PhD thesis in 1992, and namely it is called Homotopy Analysis Method HAM. Okay. Further, Hilton in 1953 came with this homotopy concept topology. And this is again reported by Singh in 1983 in the concept of topology again. So what is the relation between topology and this method that we are going to discuss while dealing with this method? So let us try to understand what is expected in this method, what we should have, and what is the scheme, and what are the steps involved of this homotopy analysis method. What is the advantage of this homotopy analysis method? The most important thing is it is what closed form. It is giving you closed form solution. Like we get the particular solution and the complementary function, and with that combination we get general solution. So in similar way here also what we'll be getting a general solution like this. So, okay. So what is HAM? Suppose that you have a non-linear problem. Okay. Generally we apply complicated methods to non-linear problems only because we seek the accuracy. Okay. Therefore, for suppose that we have non-linear problem with the u as a dependent variable and t as independent variable. So see this capital N. Okay. This stylish N stands for what? Non-linear operator. So N is non-linear operator, U is a dependent variable, and T is independent variable. It is equal to 0, means it is a equation. So it is a non-linear equation. So equation number 44 is a non-linear equation, and capital N is non-linear operator. So T denotes independent variable, and U of T is what? The unknown variable U of T. Let U naught of T denotes initial guess. Okay, that is initial approximation. So here I am calling it as guess. How to guess this initial solution that we will discuss. Okay. Now, in this homotopy analysis method, you need to define equation 45, which is what? The linear operator. What you understood from the linear operator? So you know that a linear differential equation with constant coefficient. So if your equation is y triple dash plus y double dash. So for that we can have, this is non-linear. This is non-linear, but for that non-linear, we can have a linear operator. Okay, equivalent linear operator or associate linear operator given by y triple dash plus y or y triple dash plus y double dash. Okay, any one thing in the second term. So we will remove the non-linearity term. Okay, so y triple dash first term as it is, and second term you can have either y or you can have y double dash, any one term of that two. So that will lead you to a linear operator. So our linear operator in that case will be what? dq plus d or d square. Any one thing will be there, either d or d square. But in nonlinear we have both dq plus d square. Both will be there, and due to that d square, it is nonlinear. Okay, or it is called nonlinear differential equation. So if you have a nonlinear problem, okay, given by 44, then we can claim that we have a linear operator operated on f of t, where f of t is equal to 0. Okay, so f of t here it is 0. So t is now let us construct a homotopy. So this is called homotopy. 46 is homotopy. What is homotopy? So homotopy H of phi tq colon q. So phi tq colon q is given by. So this is a definition of homotopy. Okay, and what is given? What it will be given by? So this homotopy is defined as what? H phi tq of q is equal to 1 minus q. Look at the equation number 46. In 46 on LHS we have symbol of homotopy. So it is so-called homotopy. So H phi of tq q is equal to 1 minus q. Note that if q is equal to 1, this becomes 0. The first term becomes 0. And plus if q is equal to 0, second term becomes 0. So for q is equal to 0, first term becomes 0. And for q is equal to 0, second term becomes 0. So q equal to 1. And what is q equal to 0? That we are going to discuss later on. Okay. So 46 equation is homotopy. So for any problem, this will be the style of what? Homotopy. So what is that? H of phi of tq is equal to 1 minus q linear operator phi of tq minus u naught of t. Note that u naught of t is initial guess, initial solution. Okay, plus q times a of phi of tq. What is a of phi of tq? Is that we are going to discuss later on.
Now, where q is belonging to the interval 0, 1, what is meaning of that? Q starts with 0, end with 1. And here, what comes the role of your homotopy? What is q equal to 0? Q equal to 0. Not that if q is equal to 0 in 46, if you put here, yes, you get what? Second term becomes 0. And first term will lead you L of phi of tq minus u naught of t. And if you equate this to 0, we get phi of tq is equal to u naught of t. I think that is same we are written. Okay, as a part of, okay, so if q is equal to 0, look at below 46, equation number 46. If q is equal to 0, what we got? The homotopy becomes phi of tq, q equal to 0 is equal to L of phi of t 0. L of phi of t, q is 0 minus u naught of t. Second term becomes 0. And if q is equal to 1, if you put in what equation number 46, if you put q is equal to 1, what we get? We get phi of q, we get h of phi of tq, q at q is equal to 1 is equal to, okay, if you put q equal to 1 in this 46 equation, first term whole will vanish. So first term as a whole first will vanish, leaving you q which is equal to 1. Okay, so 1 times a of phi of t colon 1, q is 1 here. So q equal to 0 is initial guess and q is equal to 1 is the exact answer. So see, as in a homomorphism, as a q varies from, there is a concept in homotopy, in topology. Okay, there is a concept called homotopy homomorphism. Okay, what is that concept? The concept is telling you regarding a embedding parameter q. Okay, embedding parameter q, as it is approaching from 0 to 1. Okay, your actual solution will be approaching from initial approximation to final approximation. Initial approximation means your u naught, and final approximation means your what? Analytic solution. So see, q varies from 0 to 1. As the q starts with 0, we are at u naught, and as q ends with 1, we are at u of t. U of t means exact solution. So see how beautifully what he has defined this theory of homotopy. So q starts with 0 and q ends with 1. So range of q is from 0 to 1. Q is equal to 0 stands for initial guess, and q equal to 1 stands for what? Final value of your answer. Okay. Now what q is doing, that again we will discuss. Now then, using 45, I think already I had discussed what I mean by phi of t of 0 is equal to u naught of t, which is initial guess. And this u naught of t is nothing but the solution of a dq plus d square type of term. And I think what any graduate, engineering graduate or science graduate can solve a differential equation dq plus d square equal to 0. It is having solution simply c naught plus c1 e raised to minus eta plus c2 e raised to minus eta plus eta and minus eta. Okay, so that is the simple solution we have. So u naught of t is with you. Okay, and it is satisfying your initial and boundary condition that you need to take care about. Okay, so if your initial condition what is satisfied by your initial approximation solution, then there is no problem with this method. The only obstacle, the only limitation with this problem or this method, that is homotopy analysis method, is what? With your initial guess. So for initial guess, I think I remember when I was working on this, I required more than 6 months just for deciding what is u naught of t. Okay, it seems very simple that okay, this should be u naught. Okay, if your linear operator is dq plus d square. Okay, anybody can see that. So it is what? C naught plus c1 e raised to what? Minus m eta plus c2 e raised to minus b eta. So a b, if you put what, we get the result, but it is not simple as it is looking like. Okay, so it is not simple. You need to struggle with initial conditions. You need to deal with initial condition, and you need to get it verified. Okay, whether initial conditions are satisfying or not. If they are not satisfying, there is no use of your initial approximation, that is u naught of t. So I am talking about this u naught of t. Okay, I zoomed in for you. So this u naught of t is very, very important. Once you cleared out this u naught of t, and if it is behaving properly with your boundary conditions, okay, initial and boundary conditions, what you can use this method very easily. Okay, because Lio on his website called Numerical Time, he has provided what boundary value problem codes in Mathematica in Maple.
Okay, in both the softwares, he has provided, even in Matlab also, he has provided the codes. So you can change your problem. Okay, you can change your parameters. So we are going to see, okay, how we can apply. So you can apply your problems. You can have your physical equations with you, and you can compare your physical equations with their physical equations, and then you can have comparison between your parameters, pertaining parameters with their pertaining parameters, and after comparison, yes, you can go for the finding solution. Okay, just you need to change the codes. If you smartly change the codes, okay, you get the answers very easily with the help of Homotopy Analysis method. So everything is made, okay, even it looks very complicated, but if you are through with your unit of t and your codes, if you adjust properly, that is a bond layer problem 2.0 dot m, that is, it is standing for Mathematica. If you deal carefully with it, yes, there is no issue with this Homotopy Analysis method. Now, as the embedding parameter, I think same I discussed now. Okay, on this slide you can see, just now I talked about what is the role of Q, that is embedding parameter. So what is Q? So here Q varies from 0 to 1, the solution phi of tq of the equation. So as the embedding parameter Q varies from 0 to 1, the solution phi of t of equation is equal to 0. Depends on the embedding parameter Q and varies from initial approximation u naught of t to the final approximation u of t. I think I already talked about this slide. So just I will, so in topology, such kind of continuous variation is called deformation. And that's why we are now going to define the deformation equations. Okay. So this is called deformation equation. Okay, without loss of generality, instead of using the traditional homotopy 46, we introduce a non-zero. We introduce a non-zero auxiliary parameter h. Okay, what is h? That is very important here. We are not going with this traditional homotopy. We are going with what? Deformation equations. Deformation homotopy equations. What are homotopy deformation equations? Here it is involving what? Along with the embedding parameter q, look at this equation 47. It is involving q, it is involving h, it is involving capital H of t, capital H also. So what? Which are which are very important as far as the convergence are concerned. H is called the convergence control parameter. Okay, so in the final stage of the talk, I'm going to concentrate on this or emphasis on this H. So this H is called control convergence parameter. Okay, and H of t is the auxiliary function. Okay, non-zero auxiliary function. So here it is written that is auxiliary parameter H. Auxiliary parameter, it is also called control convergence parameter. So there is one researcher from ISC Bangalore, P. Siddeshwar. So he has got a credit on developing this type of control convergence parameter. Okay, so he has developed, and Lio has cited him. Okay, and Lio has given credit to Professor P. Siddeshwar for recognizing this what control convergence parameter H. Now, what control convergence parameter is doing? Control convergence parameter, what is deciding the range of the other parameters to have the stability of solution. Okay, so in what range? I'm going to show you one graph. So automatically, if you deal with the programming using Mathematica, you will came to know that what this control convergence parameter range have some common profiles. Okay, and that common profiles will lead you what the range of convergence of solution. Now look at this. So this is called deformation equation. It is given by h of phi of tq, q, h, capital H is equal to 1 minus q. So it is almost like your homotopy that was defined as equation number 44. So 1 minus q, linear operator phi of t, q, h, minus u naught of t, minus q, h of t, a phi of t, q, h. Okay, and what the solution is given by h of. So see, once we got h of phi of t, q, h of h is equal to 0, we get solution of it. Okay. Now, how exactly that we will be getting? So that I'm going to show you with the help of one hands-on that we have applied for this problem, mixed conversion problem. So we have mixed conversion boundary layer equations like given by 49, 50, 51, 52, 53, and 54. Okay, 54 is a mixed conversion parameter. So here that parameter is very important. We are going to have everything based on this 54. So 50 to 53, these are the boundary layer equations, and even integer equations are also involved, and it is given by what Cheng and Minko's keys in 1977. So these equations what will get reduced with the help of similarity transformations to 55 to 63. So we have similarity equation 60 to look at the similarity equation, which is again a Falcon-Scan type of equation. What f triple dash plus 1 plus lambda f double dash plus 2 lambda 1 minus f dash into f dash is equal to 0. With f of 0 is equal to 0. What is meaning of that? There is no suction injection. F dash of 0 is equal to 1 plus epsilon, and f dash is equal to, or f dash is tending to 1 as eta tends to infinity. Now let me take again a feedback. Am I audible, Power sir?
Yes, sir, you are audible.
Okay. So given by 63, equation number 63, this is the boundary condition. So main equation that we intend to solve here is equation number 62, f triple dash plus 1 plus lambda f double dash plus 2 lambda 1 minus f dash into f dash is equal to 0. Okay, here lambda and epsilon are the pertaining parameters. Okay, so these are the parameters of the problem. Okay, so epsilon is the mixed convection parameter. Now, what is the problem here? So our operator here, if you look at equation number 62, our capital N, that is nonlinear operator, will become what? D triple dash plus 1 plus lambda, what? D double dash plus 2 lambda 1 minus D is equal to 0. So actually this is our capital N nonlinear what operator. Are you getting my point? Yes, is there any question? So look at equation number 62. In equation number 62, we have f triple dash. So that will become what? D cube plus 1 plus lambda D double dash plus 2 lambda 1 minus D is equal to 0. Is there any issue?
No, sir.
Okay. So this is the nonlinear operator. Now what will be its equivalent or associate linear equation? So see, we have f triple dash. I think already I talked about f triple dash. Here there is no linear term. There is no nonlinear term. So f triple dash simply we can have what? F triple dash. 1 plus lambda we can remove either f or f double dash. Any one we can remove to have what? F triple dash plus f double dash or f triple dash plus f. So that will be a linear operator that I'm going to show on the next slide. So look at this equation number 65. What is equation 65? What? It is a dou 3 f of eta p by dou t cube plus dou 2 f of eta cube by dou eta square. Actually, it should be cube, not p. There is a printing mistake in 65. It should be cube. So see, the linear operator here is f triple dash plus f double dash. Okay, and for this we have solution L. Okay, what is solution F? Solution of F. So look at this equation number 64. I claim that f naught of eta 1 plus eta minus e raised to minus epsilon eta, which is having same type of nature as that of 66 bracketed quantity. Okay, look at the bracketed quantity.
C1 is 1. Okay, C2, what is C2? It is 1. And what is C3? Minus 1. And what is the coefficient of eta? It is minus epsilon here. Okay, so C1, C2, they are 1 and C3 is minus 1. So 64, 65 we can have comparison. So you can see that my claim here is to prove that f naught of eta is solution which is satisfying boundary conditions of the main problem. Okay, f naught of eta will satisfy. Look at this. If you put eta is equal to 0, if you put eta is equal to 0, we get what? 1. And here also here 1. 1 minus 1, 0. So equation is satisfied. You can look at this 63 equation. F of 0 is equal to 0. F dash of 0 should be 1 plus epsilon. F dash of 0 should be 1 plus epsilon. You can check it out. F dash of 0 on next slide. F dash of 0. If you put what F dash of 0 here. Okay, first of all differentiate. What is differentiation? 0 and 1. 0, 1, 1. And differentiation of this will be plus epsilon e raised to minus epsilon eta. And if you put eta is equal to 0, we get what? If you put in 1 eta equal to 0, we get 1. And what? Minus plus. If you put eta equal to 0 in e raised to power, we get what? 1. So we get 1 plus epsilon here. So equation satisfied. Okay, so both boundary conditions are satisfied by 64. Third condition. What is third condition? So third condition is f dash of what? Infinity is equal to 1. You can check it out. First of all, you find out f dash. What is f dash? F dash will become 0, 1. Okay, and if you differentiate this, what will happen? It is plus epsilon e raised to minus epsilon eta. And if you put eta is equal to infinity, you know that e raised to minus infinity is equal to 0. And 0 plus 1 is equal to 1. Therefore, 64 satisfies all the three boundary conditions that are mentioned in 63. Okay, so f of 0 is 0 satisfied. F dash of 0 is equal to 1 plus epsilon is satisfied, and f dash of infinity is equal to 1. Okay, that is f dash tends to 1 as eta tends to infinity is equivalent. So that also is satisfied. So all the three boundary conditions are satisfied of 63 by the initial case. That's why I can claim that this 64 is the initial case. That is your u naught of t. Here I am going to call it as f naught of eta. So f naught of eta is equal to 1 plus eta minus e raised to minus epsilon eta. Okay. Now what is linear operator here? So linear operator here is L. What is equal to? What it is equal to? It is f triple dash plus f double dash. F triple dash plus f double dash. Okay. So this is linear operator. It is what? It is looking like a linear differential equation with constant coefficient, which is having a solution given in 63. Okay, under that L. Yes or no? I think all of you are agreed with me. And what? Its homotopy we have written like 1 minus QL of f cap of eta minus f naught of q is equal to QH and f cap eta, and it gets satisfied with your boundary conditions. So we are here, yes. So you can see. So we will be writing now the nonlinear operator. Look at the nonlinear operator, how we have written. So this is nothing but the first term. Look at the equation number 69. So equation 69 is what? F triple dash plus 1 plus lambda f double dash. Okay, we are exactly writing same equation. Okay, which equation? Main equation of your similarity boundary equations. Okay, 1 plus lambda f dash, 1 plus lambda f double dash plus 2 lambda 1 minus f dash into f dash is equal to 0 was the problem. So same nonlinear operator we have reported here. So this is a linear operator L, and that is a nonlinear operator capital N. Okay, so I think what now we got and we understood the relation between capital L and small capital L and capital N. Okay. On the next slide, I written a deformation equation. Okay, so L of Fm of eta minus Xm of m minus 1 eta is equal to H Rm of eta. So this is the nth deformation equation. Okay, what is Rm? So Rm of eta is equal to what? F triple dash m minus 1 eta plus 2 lambda f dash m minus 1 eta. Okay, so that is your what your Rm is. Okay, plus what summation k from 0 to m minus 1. 1 plus lambda fm minus k minus 1 eta f double dash of k beta minus 2 lambda fm minus k minus 1 dash f k dash. Okay, here xm, okay, that is given by what? Xm is equal to 0 if m is less than 1 and it is equal to 1 if m is strictly greater than 1. So I am claiming that my solution fm of eta is what looking like 74. So I am claiming that yes, fm of eta will be n from 1 to m, n from 0 to 2m plus 1 am n e raised to minus n what eta. Now if you differentiate 74, we get 75 like this. It is very easy task to differentiate this. So differentiation will look like this. And I have written here A1 capital, a big one mn is equal to minus n amn. Okay. Then 75 will get reduced to 76 with the help of the simplification that we did. And in terms of A2, it will look like 76. 76 will reduce. Okay, so there is a construction part here. Okay, why we did? For easiness in programming, what we had done all this adjustment. Okay, and after that, 76 and 74 and 76, we obtained this equation. So it will be in terms of exponential term. Every term here is in terms of exponential equation, which is given by equation 18. So once we got this fm k minus 1 eta f double dash of k, so that we will put in our main deformation equation. Okay, which will lead you what equation number 85. So what is 85? 85 is solution. If f of eta is equal to f naught of beta, which is initial case, plus the main solution fm of eta. And note that here m is starting with 1, ending with infinity, fm of eta. Okay. Now actually, definitely, and you may be thinking of it is very complicated, but no doubt it is somewhat complicated, but it is not that much complicated. We cannot do. Okay, we did it. It took some time to understand. Okay, but once you understand what it is, very easy task. As far as what we have, the codes available. Okay, if codes are available, all these are recurrence relation. Okay, if you know the previous value, we can find out next. That is the style of having solution over here. So these are all recurrence relations. So using recurrence relation concept, yes, we will be claiming that what as the n, capital N tends to infinity, what the 85, what will lead you to 86, which is the exact solution, which is the analytic solution. So this 86 is the analytic solution. And the unknowns are here, am naught, and what amn. As like that of your paid approximation, a0, a1, a2, a3, and so on, all were unknowns. Here, what these are, am naught is unknown and amn is unknown. And am naught, if you solve the recurrence relations, okay, these are all recurrence relations. So if you solve that, you will be getting am naught given by xim, which is equal to 1 or 0. Xim 2m, that is also 0 or 1, into amn minus 1, 0 plus this term. Okay, and am1 will be looking like this, and amn will be looking like this. Okay, so if you put amn in this equation number 86, and if you take capital N tends to infinity, yes, we get exact solution. And if you find f dash and f double dash, and if you put what's value of eta equal to 0, yes, you will find that there are two solutions exist. Okay, for value of lambda. So the values which are upper part of the curve, they are called upper solutions, and which are lower part of the profile, they are called lower solutions. Here we will be having a quadratic nature of solution. That's why you will be getting two solutions here. One is called upper solution, other is called lower solutions, as reported by your L et al. Also. But he has failed in explaining why he has not got the upper and lower solution for negative values of lambda. So the advantage of this method is we have succeeded in getting f double dash of 0 for negative values also. Okay, but that previous cases of L et al, he has failed in giving that answers. Okay, so that is the table. Now this is very important. So this is called H curves. Okay, so H is what? H is here control convergence parameter. Now what control convergence parameter is? Now if you draw graph of f double dash of 0 against H, you will be getting profiles, different profiles like this. Okay,
for lambda equal to 0.05 and epsilon equal to minus 1.35. This is the profile. So upper profile, then middle profile. There are 4 profiles for different ranges of lambda and epsilon, for different combinations of lambda and epsilon. So we have different profiles here, and the only common thing that you can see is a common region. And the common region you can see horizontally, it starts for h value starting with maybe minus 0.2 and ending with maybe 0.18. Okay, you can check it out. So if you see the common profiles, that is the coinciding profiles, are having range h values starting with minus 0.2 and ending with plus 0.18 or 19, something like that. So what this graph is telling you, this graph is telling you that what already Laya has proved that if h has a common range, then your solution for f double dash of 0 or for f dash or for any other things will be convergent for this range. So if you put any value, your physical solution that we obtained will behave properly. If you go outside, means if you put h value before that range, so if you put h equal to minus 0.4, yes, your solution will not work properly. If you put any value of h after 0.2, it won't work. But if you put any value in between minus 0.2 to plus 0.2, yes, it is definitely going to work for you. Okay, that is the biggest advantage of this, because it is guiding you, this method is guiding you in deciding the range of convergence of the solution for h. So Power sir, again, is there any doubt from the audience?
Yes, so participant, anyone have query, please ask.
Yes, if you have any questions, no doubt it is somewhat complicated. I have given this work to one of my students. The other student, both of the students, they are working on paid, but one of the students, what specially I have given this task of homotopy analysis method. And there are so many extensions of homotopy analysis method depending on what type of equations you have. So if you have simple equation, you can use general homotopy. If you have complicated equations, okay, maybe partial differential equations, coupled partial equations, integral partial equations, in that case, you have what H ham, S ham, okay, O ham. O ham means optimal homotopy analysis method. Okay, so there are so many things what developed by the authors like Abbas Bandi and then Anwar Hussain and so many authors like that. Yes, any question regarding this H curve? Regarding this deformation equations? Yes?
Yes, anyone have any question? Please ask. It seems to be there is no question for anyone.
Okay. So then we have, okay, so using that value of h, you can see we have graph of f dash of u. F dash of u means it is upper solution. Okay, upper solution and lower solution both in this graph. Okay, so we have drawn a graph of f dash of eta for lower solutions and upper solutions. Epsilon ranges from 0.2, 0.5 and so on, and epsilon ranges from minus 0.2 and so on like that. Okay, so this is upper solution. In next we have shown the lower solution. Okay, so that was the thing, and I think this I should not discuss here because it deals with the physical things of the problem. Okay, nobody will understand unless they have deep study of the things. So I hope it is 5 p.m. now. So I should stop at this stage, and so I would like to thank all the participants, and I would like to thank the organizers, Professor Pawar, Professor Nikam, Professor Deshmukh, Honorable Principal Dr. Kailash Karande sir, for inviting me for this wonderful FDP on essential mathematics for engineers and researchers. Do mathematics, and God exists since mathematics is consistent, and the devil exists since we cannot prove it. And last quote is regarding mathematics knows no races or geographic boundaries. For mathematics, the culture world is one country. Okay, so here mathematics is never segregating as far as your races, your countries. Okay, it is not accepting any boundaries. Okay, caste, religion, country-wise boundary. Okay, nothing is there. So we have united here. We are gathered here as a part of what we like mathematics. We found of mathematics. So with these words, I'm going to conclude my session. Once again, thank you all for listening me. There are so many interruptions. Actually, I prepared well, but I don't know at 11th moment what happened to my computer. Okay, it is not listening to me. So sorry for that. So rest of the thing, thank you very much.
Okay, sir. On the behalf of SK and Sinhagad College of Engineering, Pandharpur, I am very much thankful to Dr. Imran Chandarki sir for his detailed presentation on approximation method and homotopy analysis method. By using these methods, how we can analyze the problems. Sir has given very nice presentation about these two methods. Once again, thank you very much, sir, for your detailed session. Thanks. So with this, I'm concluding first day of FDP. Tomorrow, our first session will begin exactly at 10:30. So all the participants are requested to join before 10:30. Thank you, one and all.